I'm so excited to be in chapter 7 because now we're like taking the calculus skills and actually applying it to these biological models, which really I think is the cool part of the 17th series. Okay, so back to my original model. I had dn dt is equal to 0.3 times 1 minus n over 200 times n. So this is our differential equation, and because this is a derivative over here, that's our dn dt. We know that the way that we would undo a derivative is by taking an integral. But there's something that's kind of getting in our way. So if I look at this and I were to multiply both sides by dt, because we can't integrate something with two dn's, and I can't integrate something over here without any d something. If I multiply by dt to both sides, and over here on the right-hand side, it's kind of like I'm saying I've got dn is equal to all this stuff dt. So it's promising. We're thinking maybe we could just come in and integrate both sides, but unfortunately what's in here has n's in it, and we're trying to integrate something dt. So before we can actually take that step of integrating both sides, we're going to have to move all of the parts of this that have n's in them over to the other side of the equation. And I'm going to write this in 2 steps. So right now we've canceled out our dt's, so I've got dn is equal to 0.3, 1 minus n over 200 times n dt. And this whole part I'm going to need to take over to the other side. Well, I can't add or subtract it because all of these things are being multiplied together. So I'm going to divide it. So what I'm left with now is 1 over 1 minus n over 200 times n dn is equal to 0.3 dt. It may not be pretty, but both sides of this equation are now things that we have the tools to integrate. I'm going to do the easy side first. If I integrate 0.3 dt, I'm going to get 0.3t plus a constant. To integrate this side, we got some work ahead of us. And I really need every bit of my board space back. So I'm gonna have to erase this top part so that I can just work on this integral. Because I've done a bunch of problems like this before, I know from looking at that we're going to need to do partial fractions, but I also know that we have a choice with the partial fractions. I can manipulate this to multiply the top and the bottom by 200 right now so that I don't have a fraction kind of within a fraction. And I'm going to choose to do that because I know that in the long run, it's going to make our lives a little bit easier. So I'm going to get a common denominator inside of this by turning that 1 into a 200 over 200. And that's going to allow me to factor out a 1 over 200 in the denominator. dividing by 1 over 200 is the same as multiplying by 200 out in front. So this becomes 200 times the integral of 1 over 200 minus n times n dn. We'll remember this when we need it later. I'm going to go pretty quickly through the partial fractions here, but in order to integrate this, I would use partial fractions. So I'm going to have 1 over 200 minus n times another n is equal to a over 200 minus n plus b over n, or 1 is equal to a n plus b times 200 minus n. This one, unlike the partial fractions on the midterm, we've got nice numbers to plug in, no fractions. So I'm going to choose n equals 0. That's going to make this 1 is equal to b times 200. And if I choose n equal to 200, it's going to make that 1 is equal to a times 200. So both a and b are equal to 1 over 200. Conveniently, that 1 over 200 is going to make this 200 out front disappear. Because when I rewrite this like this, so that I have 1 over 200 and 1 over 200, I could then factor that out, and it'll cancel with that 200 right there. This will become 1 over 200 minus n I forgot my other piece. 1 over 200 minus n plus 1 over n dn. I'm being mindful of time here. Okay, so integrating both of these are both going to lead me to a natural log, but that subtraction down there, that minus n, is going to mean this one turns into negative natural log absolute value of 200 minus n. This will be a natural log of n. And if you remember, this all started with a differential equation. This was us integrating the left-hand side. The right-hand side of that differential equation, we got 0.3t plus a constant. Since n is our population, if we were solving this differential equation, maybe it'd be okay to stop here. This kind of is solved to look like time is equal to a function of the population. Usually we think about that the other way around. We think about the population as a function of time. We're going to have to do a little more work to get this to look like n equals, but we can handle it. Here, I'm going to use our log properties to combine these two together into a single natural log. The part that's negative is going to end up in our denominator. So we'll end up with natural log of the absolute value of n over 200 minus n is equal to 0.3t plus a constant. I can get rid of that natural log by making both sides e raised to a power. So I've got the absolute value of n over 200 minus n is equal to e to the 0.3t plus a constant. Now there's a trick here, and Dadell mentioned it in class on Wednesday. So the trick for dealing with this e to the 0.3 plus c, if I had something that looked like 2 to the 5 plus 3. I know that that's 2 to the 8th, but that 2 to the 5 plus 3, that may have come from something that looked like 2 to the 5th times 2 to the 3rd. Because when I multiply two things with the same base, I end up adding the exponent. Well, we're going to use that in reverse. And we're going to say that if I have e to the 0.3t plus c, that's the same as e to the 0.3t times e to the c. Because c is just a constant value, if I take e and I raise it to a constant value, that's also equal to a constant. So the trick that mathematicians usually do is to just call this some new value of c. They're not the same c, but since we haven't actually solved for what that constant is, instead we'll just replace it with this constant and deal with this constant. Okay, again, I'm running out of board space. I need a whole classroom worth of chalkboard or whiteboards. Okay, we're looking at n over 200 minus n, all inside of our absolute value, is equal to, oops, we're going to use that trick and have our c e to the 0.3t. I've been really careful to keep that part on the left inside of the absolute value this whole time. And I'm going to flip my board around for a second because I want to remind us that the nature of what happens in the curve is different depending on whether we start with a value that's less than 200 or we start with a value that's greater than 200, and how close that value is to our carrying capacity in terms of whether we're going to see this inflection in the curve or we're only going to see that exponential growth or decline. Well, looking back to this problem, if our n is a value that's less than 200, then we don't need the absolute value anymore, because if our n is less than 200, this will already be a constant. So right now, I'm just going to focus on n values less than 200. So I'm going to say that we're going to specify we're thinking about n being less than 200. So I don't need the absolute values anymore. And I'm going to rearrange this to make it say n equals. So I'm going to multiply both sides by this term so that I've got n is equal to c e to the 0.3t times 200 minus n, and then distribute this out. So n is equal to c e to the 0.3t times 200 minus n c e to the 0.3t. Now, my objective is to get the n by itself, so I want to move this piece to the other side and look at n plus n c e to the 0.3t. And I'd still have this piece over here, so that's 200 c e to the 0.3t. I'm almost done. I'm going to factor that n out, and I'm going to do two steps at once. I'm going to factor that n out and then think about dividing the term to the other side. So when I factor the n out, I'd have 1 plus c e to the 0.3t. So my n is going to look like 200. Oh, I missed my C. 200 C e to the 0.3 t divided by 1 plus C e to the 0.3 t. This is our solution for the population as a function of time, but sometimes there's another way that this formula gets manipulated, and sometimes we divide every term by e to the 0.3 t or by c e to the 0.3 t. And I'm going to go ahead and divide by that c e to the 0.3 t because I think it's easier to see what's happening to our limit then. So if I divide everything by c e to the 0.3 t, I've got 200 and 1 over c e to the 0.3 t plus 1. Or, because that c is just a constant, 1 over c is also a constant. It's not the same constant, it's a different constant, but I could say that this looks like 200 over c e to the negative 0.3 t plus 1. That defines the shape of our logistic curve. This defines that shape that kind of looks like a cubic on its side. Now, thinking about the numbers, as t gets very large, or what's happening to our population after a very long period of time, when I plug in infinity for t, essentially, I've got e to the negative infinity, which means this whole piece is going to 0, and our population is approaching 200 after a very long time.